Hello, everyone. My name is totally not a Haxer or Ryan. Ryan is much more preferred because a lot of people can't go on with Haxer. I'm a reverse engineer and software developer, and I'm 16 years old, and this is my presentation on reverse engineering and cracking code. This presentation isn't going to be so heavy. I'm trying to keep it beginner based for people who don't really know much about reverse engineering, maybe people that know it exists but don't know the deep depths into it. Um, for background on my experience, I spent a lot of times in game hacking and game cheat development and even exploit development. And currently, I'm studying software cracking, basically breaking applications. And that's what this presentation is about. So the actual point of this entire presentation is to talk about how reverse engineering works, cracking code, what exactly is it, and then we go through a bit into theory and then the internals of programs and applications, and even touch on the assembly programming language. The last two sections, I mentioned this a while back, but we will not be going over those two today because I think the presentation might go on a little bit too long for that, and I kind of want to section it into courses that people can actually understand into a point where it's not rushed. So this part will just be about the fundamentals about reverse engineering and everything. So without much more to say, we can go ahead and head into it. And the first thing I would actually like to start off with is the introduction to reverse engineering. And that there would be a few different concepts that I like getting people used to. What is reverse engineering? Like hacking and cybersecurity, reverse engineering has many different meanings, but the primary aspect of reverse engineering is taking an application apart, reversing its functionality to either understand the application or bypass specific fundamentals or parts of that application's security systems or really whatever it can be. In the case of cracking code, you are typically going to be bypassing security systems or cracking past those systems, building key generators and stuff like that, which we will get into a little bit deeper into the presentation. The purpose of reverse engineering. This is one question I get a lot, and I try to spend a little bit of time on it, but there's a lot of reasons that reverse engineering exists. Typically, everyone just starts off reversing random applications, but then it can also go into malware development or malware analysis. There's a bunch more aspects that go into it. I know RE helped me understand the proprietary software that was owned by Apple for Apple products. I basically did IoT research on Apple TV, and reverse engineering helped me understand the way the binary formats work, the way data is transferred, even as well as how the protocols work. Um, Another major purpose of reverse engineering is to be able to identify major security weaknesses or vulnerabilities inside of applications. Um, One thing that comes across a lot in binary security or just applications as a whole is that the actual security of the application itself, when it comes to the executable, is what you can say, or binary, isn't taken as serious as it needs to be. So the point of reverse engineering can say, okay, hey, I found your API key in plain text. Let's patch that or let's encrypt it. Or hey, I was able to bypass your login restrictions with a debugger. Let's add anti-debug protections, which again I'll touch on a little bit more. It can even help in understanding legacy systems. Like most banks use COBOL and Fortran 95 still, even though we're in 2023. And if protocols or systems aren't well documented, then reverse engineers can also help by dissecting the program and understanding what's going on so they can better document it for themselves. Then you have the methodology methodology behind reverse engineering. There's a lot of aspects from it, mainly depending on the field, but they do kind of all have their own primary aspects. One thing I like to point out is that reverse engineering has a lot to do with the internal of an application. If you want to reverse engineer something, you are going to be digging into the internals of an application. Now, of course, when it comes to debugging and stuff like that, that's all basic disassembly. Even debugging is what you're going to be looking at. But there is also a little bit, if not a ton, of dynamic analysis within a program, or I guess steps that you do it with. Personally, for beginners, I call this internal and external analysis. Static and dynamic analysis have their own technical terms and they're meant for that. But for reference to this introduction, cracking code, and stuff like that, I will be referencing static damn, 1 second. Static analysis as internal analysis, and then external analysis, or yeah, external analysis will be the dynamic analysis. I flipped those. But geez, yeah, already messed up on that part. But the external analysis will be the actual dynamic analysis side of things, and the internal analysis will be debugging it and digging deeper into the internals of the application, or the static analysis of the program. Excuse my mistakes there, mixing it up. Another major part of it is going to be your documenting and your changing findings for applications. If you are cracking software, even reversing applications, one thing you're obviously going to do is want to document everything that you're finding. The documentation part of everything is important, so you can remember exactly key points in the program that you need. In the case of you can't crack code, which again, going back to key generators and stuff like that, you will need to know down the algorithms and stuff that they are using to generate or assume license keys in the application. There's a whole bunch of different methodology behind it, but the main one is going to be your reconnaissance and then documenting or changing your findings within the application in appliance to cracking code. Now that we have that down, we can actually head off to the terminology. This I have a decent list for, actually, that I wanted to talk about. But software cracking, as we already went over, it has a bunch of different meanings, but mainly, when you do crack an application, you are modifying the internal systems that exist within it, whether it's a login system or even just a simple music system. Cracking is typically defined with bypassing the login system, but because of those differences there, it's kind of hard to say what exactly the definition is. Other than that, it's up to interpretation of most people. But in this case today, or this whole presentation, it will be saying cracking software for login systems, and that's what we would bypass, and that's what we would crack. Next thing you know, you have the codification. Codification is a concept that it seems like a lot of people can't grasp properly, maybe the actual mathematics and the side behind it, which we won't go into. But codification, pretty much the act of hiding code from what you can call an adversary who is trying to disassemble your application and learn about it. Codification basically takes the existing code in the application and hides it. They dig it up using specific algorithms, or they find ways that you can basically mix that code up and make it seem very hard to guess, I guess is the word to put it. The next term I'd like to go over is decompilation. I heard this sentence, or I guess phrase, a while back, and someone told me that you can't decompile a program until I looked this up. Decompilation is not necessarily taking machine code and just decompiling all of it, but it is basically taking the application, dumping it into something like IDA, which will dump the assembly of it, and then translate that existing assembly into pseudocode, which is not necessarily the entire code of the application in every laid out form, but it does give you a good base of the decompiled binary that you would see. So it would translate to a native language like C or C++. This helps because it can help us understand what an application is doing logically instead of having to sift through thousands and thousands of lines of code in assembly at that point in a RE framework like IDA, or even a debugger as much. It is very painful to do. Patching. Patching is a term used to typically describe when we take something in an application and typically edit the assembly. For my terms, when we would patch a binary, we would replace specific lines of assembly or even fix up some lines of assembly in that code. And in this case, the cracking code, we can take the binary, dump it, and then patch specific instructions to bypass login systems or key systems or various other things. The dynamic analysis part is something I actually have a chance to better define. The dynamic analysis of an application is taking the application in itself and going through the steps of what exactly that application is doing in its active state, not its static or its held state. So typically, you would open an application and understand what's going on dynamically. What happens when you click certain buttons? Is there a specific set of inputs that we can throw into the program that makes it crash, or is there a limit, character set, and so on from there. This helps reverse engineers because it helps us understand what exactly is going on in the application on the outside and what to inspect or to look for on the inside of the application. This then transverses into static analysis, which is the analysis side of things where we statically analyze the application, which means it's not in its changing state. The application is simply just ran through a debugger and is running in your step-by-step statically analyzing the application. This step is seriously when like everything from dynamic analysis kind of comes into play, because all that logic we learned about how the application works, we can see if we can find it in the debugger we're using, or the reverse engineering framework, or even whatever tool you are using to statically analyze an application. When it comes down to software cracking, there is a lot of tools out there. A lot. There is a lot of universal cracking tools that can help you auto patch or auto generate keys for specific softwares, and sure, most of them are malware and you might get ransomware in a little bit, but that's just the part of it. But you also have frameworks that are dedicated to helping find you vulnerabilities in an application to help you better crack or even better analyze that tool or that program or application, whatever you want to put it, so you can reverse engineer it. Unlike cracking tools, you also have the reverse engineering frameworks, which are the frameworks like Ghidra and IDA. I'm sure most of you in here are very familiar with those frameworks. Those reverse engineering frameworks help a lot because they can give you an outline of the assembly, dump everything, they can search for strings, they can find practically everything you want in a binary, as long as you know how to use it. These frameworks are a bit different than cracking tools because they don't actually help you crack them, they just help you understand the application. They are reverse engineering themselves. And then you guys know, I think pretty much everyone in here knows what a 0 day is, but for the ones watching that may not, a 0 day is a type of vulnerability that developers are not aware about. So if you find a buffer overflow in a binary application and the developers don't know about it and it hasn't been reported, it's considered to be a 0 day. Right, so that is it for terminology, and that should give us a base start to everything. You might come across some terms that we're going to use in this presentation, and the set of presentations throughout everything, to make sure that we can kind of get it in our heads and get it filled. So now we have the one thing I talk about a lot. What does cracking code exactly mean? As we talked about before, cracking code has a defined definition, but cracking code in its own terms is just cracking the software. Going to bypass restrictions, modify systems, or dig inside of it and make a patch inside of the application. That is actually pretty much the best way to put it for this case, and I feel that that was a good way to go over it instead of getting it confused with different terminologies, different definitions, because there is a lot of definitions that people have on their own that are a bit wrong, but at the same time apply to only those specific scenarios. But definitely, cracking code is simply just exploiting flaws in an application by reverse engineering it or patching it. Then you have limitations of cracking code. So in this case of what we would be cracking today, or maybe not today, but in another presentation, as I mentioned in the start, there's a lot of limitations that come to modern day software cracking. You're not just gonna go up on CrackMe and just crack a few cracking challenges and then just outcome cracking PowerPoint or some extreme enterprise license, because these enterprise frameworks and enterprise applications have a ton of protection mechanisms in them that prevent you from even slightly viewing the process information of the actual application. They can do this, which in this case would be an anti-debugging technique. Before a reverse engineer can even come close to actually cracking the application, some people, and most people today do this, they will find ways to block any form of debugger. If a window, for example, has the name debug or dbg in it, then it might just quit and kill that process. In other cases, you might see that they actually listen on the threads of your operating system and they check for very specific signatures, or in the case of debuggers, they may also watch to make sure that you are not creating a handle or you are not attaching a debugger to the process. There's many ways to do it, but that is one way or a good three primary ways actually that developers can prevent reverse engineers from patching or breaking past security systems. The next thing we actually wanted to talk about was code integrity checking. This is probably one of the more better methods because instead of blocking a certain debugger or watching for methods and stuff like that, you are actually preventing the reverse engineer from attacking your application by preventing them from just changing code. Code integrity checking for beginners is pretty much just a system that checks the integrity of specific files or signatures in the files and addresses and makes sure that everything is the way it is. And if it's not, then the application may quit and say either this was a violation of so-and-so security system, or they may just tell you to re-download and reinstall the version of the application. This is a very challenging thing to get around, but then there's other methods like key generation that can also bypass this, because instead of messing with the code yourself, you are just generating keys for that program. Again, we'll jump into that a little bit later. One thing I also felt I needed to talk about a lot more in my presentation was how programs work. One of the common aspects to programs and even reverse engineering in itself is learning how everything works on the back end. A majority of what you're going to see in reverse engineering when you go to dump a bunch of source code, or you go to read module files, or say you're even hacking a game and you have to look at game file, most of what you're going to see is either assembly, custom game configuration, custom application code, or some form of texture that you just can't exactly figure out what's happening with that application. Having a fundamental understanding of what happens behind applications, such as the compilers and how compilers work and how source code works, is a great example to show you and tell you, hey, what's happening, and here's how we can go about attacking our application. For me personally, and everyone learns different, especially in reverse engineering because it is such a vast field, learning not only how programming languages were built, but even coming from experience and building my own, not saying that you have to, it helped me a lot understand how interpreters work, how bytecode works, and how machine code works. The deeper understanding of machine code helped me understand, hey, this is assembly, this is normal, this is on this architecture, and what the application may be doing all depends on the type of code they have or what architecture they're writing the code for. Even in languages like C and C++, you can compile it for a very specific architecture, which will change everything. So having a deep understanding of how the programs work is a little bit something that's good to talk about. In this case, we have a compiler. Let's say we have a language like C, or typically your average Windows applications are written on a C++, at least for now. And C and C++ have a whole different process of things. They basically take an input source code file, or source code file, throw it through the preprocessor, and look for these macros or preprocessing definitions, which if anyone's ever developed in C, you can say like include file.h would be considered to be a preprocessor, or even something like pragma once is once would be considered what the preprocessor would look for. They're basically pre-processing instructions to tell the program or the compiler what to do when you're working on compiling the actual program. When the source code is done going through the preprocessor, it goes through the actual application. Excuse that. Oh, jeez. Right. So once the preprocessor is done, it will throw it through the compiler, and the compiler has a whole set of different things inside of it. It has different steps such as lexical analysis and tokenization and parsing and all these different steps that really go into the compiler that can make it better understand the source code that you're handling it. Because if you declare a variable in something like C or C++, the way you declare it is not going to be the way the compiler sees it, because the compiler has a whole step for tokenizing data and creating its own structure to better parse it. Once the compiler is done throwing through all that data and actually properly parsing it, and then throws it into the what some people would call translated or generated code. The job of a compiler, which a lot of people think is to just compile straight down to machine code, and compilers don't do that. This is because there's a lot of issues with just compiling straight down to machine code, in at least aspects of where C and C++ were developed, and a lot of performance issues were main concerning. So instead of that, they actually would take the architectures or the instruction sets of architectures like x32 and 64, and would translate them or generate code from the source code that you gave it. Generate these assembler files, which would then go into the actual assembler compiler, which would generate these object files, parsing through the linker, and then generating a final executable. All this code that is generated throughout the whole process is, in its own way, a little bit different than you might think. Because again, everyone does think that compilers go down to machine code, but it's important to know that they don't. Because if you can ever get into assembly, or you're looking at an assembly dump, the factor being that you can't really decompile everything into that form, because it's not actually the compiler that is translating everything. I just wanted to get that base down a little bit and talk about how those programs work, again, for the purpose of the factor that knowing how applications work is pretty important in RE. And in the more the logical comprehension things, it will help a lot more. The next thing I actually wanted to go deeper into was how different programming languages work. So you have these, how do I put it? You can literally just say memory. Computer memory is something that a lot of people miss in programs. They know it exists, but they don't exactly know what the direct point of it is. And I have this whole thing set out where we're going to talk about stack memory and heap memory and what it is. But first, what exactly is memory? By definition, memory is considered to be a fundamental concept in computer systems and programs, which refers to the ability of a computer to store and retrieve data for processing. Memory for computers, it plays a major and one of the most crucial roles in executing programs. Storing data and facilitating communication between different components of the computer you're running the application on. Memory helps a lot by storing those variables and making sure that programs can remember what's happening. This concept here also spawns into two different types of memory. You have the memory that consists of multiple types, which can serve their own individual unique purposes. In this case, there are two main types of memory, which are commonly used, which are known as stack and heap memory. Before we get into heap directly, I want to talk about what exactly stack memory is. Stack memory is considered to be a region of computer memory that is primarily used for storing temporary data during a program's execution. So think about a program that you have that's in like C++, and you have a function that is called a few times throughout the program. A better example can actually be, I'll write a example Python script for this, say call, and then we have another call2 here. If we call1 through the, just by calling it, it's going to be pushed onto the stack in the memory, and then will be forgotten about once it returns. The stack memory basically helps by keeping track of every single variable under call or call2 those individual functions. And once those function returns, everything is just pretty much forgotten about. One important concept to notice that we actually go into after this is going to be the LIFO principle, or the last in, first out. It's also known as FILO, so first in, last out as well. But the LIFO principle is basically meaning that the last item that is stored in a stack is the first one to be removed. I go about that a little bit more deeper into detail, but basically the stack memory is just important for keeping function calls and function traces, or even local variables for those functions, and keep track of them for the current state of their lifetime. One of the major things that I guess are mainly pulled into stack memory or released is the local variable storage. A lot of people forget that local variables can be stored in a stack. And in this case, as we talked about before, the one thing that the stack is known for storing is the local variables within the functions, within the scope of a function. When the function is called, the local variables required by the stack are technically considered to be loaded, or in other words, allocated onto the stack. You can think of it like this. Say you have like a stack of papers already. The general form of the paper stack represents the entire memory stack. Every time you load a new function, we place a piece of paper onto the stack, which is known as a stack frame. Each stack frame contains vital information and is dedicated to storing the function's local variables, function arguments, and bookkeeping other information. These stack frames are extremely helpful and required for programs to keep track of those functions directly separately. And it may even store data such as the return address and the parameters that are used within a function. Basically, to clarify fully, the stack frames are specific sections within a stack that hold the information relative or related to individual function calls. That is pretty much how the local variable side of things. The function call information as well as even stored on the program. Like I mentioned before, when the function is called, the information is put onto the stack, to the stack, such as the address or return address of the function and arguments and parameters. That would be the function call information that would be stored onto the stack frame. When the function is done, it is popped off of the stack, um, basically saying that when you do complete the function call, that stack frame is then removed off the stack and then pretty much forgotten about. This is why in programs, when you go to run a C file and you have like a, say, X under function A, you can't actually access the variable X under function A until you are under that scope, because it's not really a global variable and it's not remembered for the entirety of the program. It is only remembered for the call of that function. So once that function call is over, that's pretty much it, and the variable isn't even known anymore. Um, that is kind of another thing I actually wanted to go into, was the lifetime or lifespan and scope of stack memory. As we talked about before, we have all the variables that are allocated on the stack and have a very different lifetime depending on the scope within a function. Once the function finishes executing, there is no more time for those variables to be saved or no reason for them to be used unless they are being returned. Variables and arguments and other information that was stored on the stack frame, once that stack frame is popped, it's automatically deallocated from the stack. The reason this happens instead of just saving it basically ensures that the resources are released properly, ensuring that memory leaks won't happen, and that we can also improve overall the system's performance. Um, the same concept that goes to say that it is popped from the stack pretty much as well, um, when we are removing that function, just to go over that again. So stack memory in terms is just a way for functions, return addresses, and different things to be stored, and is a way to store stack frames of very specific scopes of code. Now, the cool thing about the stack memory is that the programmer doesn't actually have to manage it. The compiler or the executable, whatever is stored and is running that application, is pretty much running stack. The good thing about this is that there's a very small, less likelihood of the stack just overflowing randomly. Because even though the programmer is writing the application, the stack isn't managed by the programmer, which means the programmer doesn't have to manually release or free memory. In this case, that's actually where we go into the dangers of heap and what exactly heap is. So unlike your stack memory, your heap memory is completely controlled by the programmer. Basically, in the scientific terms of things, it's just another region of the computer's memory, but instead of being the whole statically allocated, it's dynamic memory allocation occurs. The heap memory is also not set by the compiler and does not have a static or set range of data or amount of storage directly, and is also not automatically managed. I mean, as we talked about. Instead, it all completely falls to the opposite. When we talk about the developer having exact control over what the heap is, one thing we can think about this way is like, what do we mean by that? Well, instead of the compiler saying, hey, let's free memory in this section of the stack, or go on from there and just free or release or even allocate new resources, the programmer has to use functions that are built into the programming language or use specific methods to free the memory that they use up in the program. When you want to allocate functions or not allocate functions, allocate memory, you have to call allocatable functions. Functions like in C++ called malloc or memory allocate. And when you're done with that memory, you have to free it manually. The issue with Heap is that while it's very great for flexibility and it has a lot of room and there's a lot of things you can do with Heap, more than you can Stack, the memory fragmentation and what's known as memory leaks will also occur. As we discussed before, as you guys are mostly all familiar with, programmers and developers, they all make mistakes. You hop into an application, you find an SQL injection vulnerability, and you realize, wow, these developers made a mistake by not sanitizing input, or not securing a server, or not having proper protection methods to prevent them from seeing that vulnerability or those issues, or even being able to exploit it. The same happens in programs. Instead of forgetting to implement a security mechanism, which does happen, um, developers, in the case of heap memory, will just forget to free memory. When this happens, the danger that comes with it is called memory fragmentation. Basically, memory fragmentation is when the free memory in the system or the program becomes divided into these small, non-contiguous blocks over time. This basically results in a, I'm trying to think of it, it occurs as a result of memory allocations and deallocations, leaving the gaps or the fragments of unused memory completely scattered through the memory space. The heap is also susceptible to the memory leaks if the programmer does also not watch how they allocate or deallocate the data, or even use data. There's a lot of times where you're working with heap and it's not even allocating or deallocating the data. Sometimes you can create the wrong data type conversion, or something can go wrong where it corrupts the data or memory leaks out of your system. There's a lot of other reasons as well, such as advanced threading that can go on with that, but that is still all down to the programmer and what happens. Um, to sum up, pretty much both the heap and the stack are very extremely vital, important segments of memory that can help computer programs execute the way they do. How they can remember variables or remember specific things in the application that are vital to the program or the application. It is literally memory. Since the program needs to be able to help remember there is a variable there or here, um, there needs to be some form of stack or set of memory that it can store the data in. And without that, programs pretty much just have no memory. Um, they both do have their own disadvantages and their advantages, but my, I guess you can say primarily to say that they're still very vital, and there's a lot of protection mechanisms that can go into place. And plus, there's a lot of compilers out there that all have security methods built in to say, hey, the programmer made a mistake when working with a heap. Or even if you get a Stack Overflow, something, there's a lot of systems in place in advanced technology now to tell us when we made a mistake. Now, of course, you can't just like open the biggest project in the world and then it automatically catch the error, but there are systems to help out with that. In the case of Go, Go has its own panic system as well that lets you know if there's a specific memory error that is happening within the application. So next thing we have, in this case, will be going into the LIFO slash the FILO part of everything, and these two terms are pretty vital. So a while back when I was talking about stack and heap, I talked about the first in last out or last in first out. Um, Basically, this means for pretty much every single variable, or I guess you can say anything that is pushed to the stack that is first will be the last to be pushed out of the stack or popped from the stack. Um, this application really helps understand when variables need to be popped or the organization and the setting of specific things. In the case of heap, this is also really helpful because programmers can better leverage this to understand their knowledge of how the stack entirely works and how heap works, and actually control memory from there. Now, again, the stack actually can be controlled by the programmer, so you're not going to be using like deallocate or allocate or memory allocate on a stack, but you would be using it in heap. I have this Perl program that I can actually show you guys that I use to represent it. Um, Perl is one of the better languages I felt I could actually explain this with. It's nothing too advanced, so you don't actually need to understand the programming language to understand what is happening. Um, Here, let me actually pull this image up right here. So this is a simple program that starts a stack. Pretty much, we create an array, and that little my at stack is the array. we push items into the stack. We push three values: apple, banana, and cherry. Because apple is the first in, apple will be the last one popped from the stack. We push banana and cherry and so on from there. And basically, our stack consists of those three variables now: apple, banana, and cherry. Because this is an array and this isn't exactly how directly stack is, this is just a good way to represent the pushing and the popping. Now we want to save the variables from the result of the pop. So we pop one value from the stack, so pop will return that last or that first thing. So it'll be cherry, and then we pop the second one, it will be banana, and then we pop three, then we will pop the last out, which is cherry. Or sorry, apple on that case. So our first item that we popped from the stack was cherry, our second item was banana, and our third one is apple. This can represent this actual, the stack, the first and last out concept, and the LIFO concepts, because the array method actually shows us how the pushing and popping works without actually having to directly mess with the memory in another program or some advanced concepts. So this was just one way that I felt I could explain it a bit more, because even I got very confused a little bit when I was learning about the stacks and stuff. Even now it's still a bit confusing to get. I mix it up a lot. But outside of that, now that we have that down, we can actually move on to our the assembly programming language. So before we actually start on this slide, I wanted to clarify something. When it comes down to reverse engineering, I talk a lot in my articles, and since this is a presentation pretty much on the article, I talked a lot about the theory of applications, the theory of assembly, the theory of logic, and then how everything boils down. When it comes down to logic, that theory helps you build a direct fundamental skill set that can tell you exactly what is going on within the application without directly looking at it. So in the case of what I tried to teach to people is tell them that learning things like how to understand how control statements work, like if, else, if, or even learning how variables work and data types are stored in programs can really help you build like your own kind of logical gate that will tell you what's going on in your head if you see something in an application. Like in our case, if we go to a browser and we type a bunch of words and then hit enter, we can say there's an if statement that is probably going to be checking the length and so on, and or the amount of words and picking different values out. That theory really helps you grasp common concepts. Now that we can actually go forward into things, and we know the smallest amount of applications and how everything works in a base fundamental, we can hop into assembly. This was something that I felt was super important to go off, because a lot of people don't actually think assembly is needed, even in today's world still. So since the assembly programming language is kind of a large thing to go over, I have summed it up in a few things. So what exactly is assembly? Assembly is considered to be a low-level programming language, primarily because it has access, or is considered to be close to the metal, because it gives you this like bridge between the high-level components and the low-level of this components of a system, such as the I/O utilities on a CPU, for example. Unlike most high-level programming languages like C and C++ and even Go and Ruby and Python, you have assembly, which is very, very platform specific. It's very architectural dependent. I guess you can't say platform, you should probably say architecture dependent more, because it basically relies on the architecture of your CPU. If you try to program x64-86 assembly, for example, for a 6502 microprocessor, you're obviously not going to be able to run it. You might be able to compile it with specific tools, but there might have to be emulators on your system for you to do that. Even then, executing it natively on a 6502 just won't work because it's a completely different architecture. When it comes to working with programs and working with assembly, you will also notice that you have to understand each individual CPU architecture or set of what they're called registers, which we will get into later to actually help and understand that program or write our program. The thing with assembly, and this is something I've come across a lot, I've come across this argument too many times, And it was a lot of people saying that whether it's not, it's either assembly or assembler, and what the difference is between the two. If you hear assembly versus you hear assembler, and then you hear someone who says, well, assembly is a classification of programming languages, they might slightly be wrong, but they're not too far off, and it's a very big debate still. Again, that I hear, you might not hear the same thing. But for context of this place, we will just say assembly after we are referring to the architecture of the CPU. So instead of saying just assembly 86, you would say x6486 assembly, or in the case of what I said, 6502 assembly for the 6502 microprocessor. Um, so the part with the assembly programming language, I've mentioned this multiple times, but I think I should kind of clear up a few points where I didn't go full into it. Why is it helpful for us in reverse engineering directly? Primarily, if you want the easy answer, it's because really everything we look at is going to be assembly. Whether you disassemble a simple application, I mean, you can even go down as far as disassembling a small binary. Whatever it is, you're still going to see assembly inside of it, no matter the architecture, because even languages like C++ and C again, they don't compile directly down to machine code, but they translate the instructions from their high level perspective to the equivalent instruction in the architecture and generate bricks off of that. Again, there's a whole missed code section that goes through that, but because of the scope, we couldn't really get deep into that. It's helpful mainly for us in RE because it can also give us this easy way to translate applications or understand them. Even if it's a bit harder and you're not going to go through thousands and thousands of lines, and high level code is definitely better, it's still helpful to understand assembly so you know what you're looking at when you dump a program, or you're looking for a vulnerability, or looking for some way to bypass a restriction in our case. Um, it may also be considered to be used for critical tasks. Even if you don't fully learn it for RE, you're still going to want to find some way to learn it and apply it to other aspects, because assembly is probably one of the most hated programming languages, but the more you get into it, the more you're like, wow, this language actually teaches you a lot. Because most of the names and the registers and even the instructions in assembly are quite easy to understand once you get the logical idea of what they're trying to do. Um, and with that, that is kind of why we use it for RE. It gives us this base of logic about a program, and it can help us understand how everything works. Um, Next, since we're kind of past the assembly point, there's different types of assembly, as I mentioned. You have your x86 64-bit assembly, x64 32, 6502, Z80, and then other versions of the assembly programming language. You even have ARM. Each architecture, each what considered to be a platform with CPU, not CPU directly, but CPU's architecture does have its own version of assembly. The primary difference is in the way the assembly operates with the actual CPU, the registers that it's giving you, the ability and the calculations it can do, as well as the functionality around that entire architecture or platform. Uh, for example, again, going back to the x64 to 32 or x86 to 64-bit assembly, and then looking at like 6502, you notice that they're 32 and 64-bit x86 assembly versus an 8-bit CPU. For context, the 6502 is an 8-bit CPU. Its registers are completely different and can't really process the amount of high level that the 32 and 64-bit architectures might need. Same with the Z80. Z80 assembler has a whole different structure to it because it is an 8-bit microprocessor. Um, for context, Z80 worked on the Xylong Z80 microprocessor. That was just that processor's name, just so I'm clearing things up a bit. Um, and then each processor was also used for its different things. But in relation, it doesn't really matter what type of version of assembly it is. Typically, assembly is going to be known as a programming language that gives you this bridge and direct access to the lowest possible side of the system outside of machine code. Which is why I even say when someone says low-level programming, you're not really doing much low-level programming unless you are either doing it in straight machine code, which I don't think anyone does today, and you're working with the assembly programming language. You can do some aspects of low-level programming or what can be considered to be low-level. It all depends on the context. If someone says, hey, I'm working with a microcontroller and I'm using assembly with C++ or inline assembly with C++, or even working with Arduino, there's a lot of considered points that can be considered to be low level there. But again, the context does really matter. And without context, you can say that pretty much the only two types of low level programming languages will be machine code in assembly or assembler. Um, so the primary difference there is really just in the structure or the architecture of that language that is there. Um, so why assembly? Why do people use assembly for their purposes, or why may they even want to go into it? Well, as we discussed, it's not really used for primary development. It is. It is definitely used in a sense, but it's not as the way you would think primary development would be. Most people very rarely anymore build entire frameworks out of just assembly. You will definitely see it, but you won't see it as much as you will see 3,000 code files of just C++, or even something as much as like 40,000 Python files in some weird database or system. This is because assembly is a very, very long programming language to learn. It's very tasking and it's very platform dependent, and that is a very big con when it comes to working with big projects. So in today's world, mostly assembly is going to be used for smaller things like drivers or shell code or exploit code, or even reverse engineering. And when it comes to those specific aspects, that's when it becomes super useful. Again, you still definitely see that people use assembly every day for certain specific code topics, but those topics are also kind of, again, very specific. They're not going to be used for your general purpose programming like Python, R script, Perl, or even Go would be, or in this case, C and C++. Um, so that is kind of just really where it would be there. Educational purposes. In our case, we are learning reverse engineering, so we kind of need to pick up on what assembly is and what exactly that language does, and even need to understand the direct hardware purposes of the language, what it can actually give us in terms of RE, and why it has this direct connection. Another thing to mention is that the mnemonic programming, that's just another aspect to say that it's very low level, and it gives you direct access to those utilities such as the CPU registers and the IO utilities and more. There's not really much we can go to expand on that as far as without going into advanced assembly, but that is definitely one way to kick it off. Next thing I actually wanted to talk about is go into registers of a programming language like assembly. Because assembly is one of those programming languages that uses CPU registers directly, we can actually talk about the general purpose registers, which is our next thing. Before we go on to learning about these different types of registers, I kind of want to explain a little bit what a register is. Pretty much for the most basic terms, registers are just the special locations within the processor that can be used to store specific types of data, or they can be used to store specific items. For the case today, in the case of the crackme, actually, that we would be cracking or working with, it's written out of x32 64-bit assembly, which will be common in that application. So for today, we're going to be learning the x32 and 64-bit version of assembly and going about the registers used in that version. In other versions, I will talk about x64-bit assembly. That will be a different story because we'll be diving in into a different program. But that is one exactly good way to get into it. So what are these registers here? Well, for starters, they are just general purpose registers, and those registers are used to store that data. In this case, we have the first register that we see, which is our racks. Um, there was one I actually had here specifically, if I can actually just pull it up. Let me see if I have it in my notes. Because there was one I actually wanted to talk about. So the racks is just going to be a different register for storing data. It is an accumulator. It would be used for specific operations like mathematics or storing data. In other cases, you may also see EAX, which is actually something I had there before that I released. And EAX is another thing that's primarily used for arithmetic and logical operations. And it's typically the default register for storing function return values. So in this case, a usage of EAX would actually be like, say we wanted to add the value of EBX into EAX, we would say add, geez, add the value of EBX into EAX and then push that into the contents. So it would basically add the contents of EBX to EAX and then store it in the EAX register. Then you have our next instruction, since these are pretty small, the ECX, EDX, and the EBX. I have this as R. I think I was working with the wrong type of assembly. They're still hold their same values. So in this case, we're actually just going to be going with R or E. The base, this is known as the base. The EBX register is often used as a base pointer for the memory access, and it's basically just that other general purpose register. We can use this to actually store specific hex values. So we can actually use the move instruction to move, say, 1, 2, 3, 4 hex. I guess 1, 2, 3, 4, 1, 2, 3, 4 hex, and then we can actually go back here and say move it into EBX, and then it would store the value of 1, 2, 3, 4 hex into EBX. This is also RBX, but because this was a different version of assembly, it kind of nulled out. The ECX, which is just RCX in this case, it is a counter. The ECX register is commonly used pretty much as a loop counter or some sort of shift rotation for operations. An example of this is looping through an array and then basically making a counter. So we can say, let's move 10 into ECX or RCX in this case. So say move ECX and we'll say 10. If we were iterating over a loop or something like that, we can say that the counter ECX, or in this case again RCX, will be the counter representing the number of iterations that loop will need to take before jumping back or going through conditions or returning. Then you have RDX in this case, which is our EDX. The EDX register is used for extended data operations, such as a high order of bits of manipulation. We can actually use this as a good example to represent the multiplication of integers using the IMUL instruction. It pretty much looks like this. The IMUL instruction just stands for integer multiplication. Basically, add or multiply two numbers and then store it in a specific register. So let's say if we wanted to use the way EDX works, we would say IMUL EDX, or in this case again RDX, and then into EAX in 5. This will basically multiply the contents of our the values stored in EAX by 5 and store the result in EDX. Something to clarify here, and something that helped me a little bit, is to know that the first register is typically the one you can store in terms of addition, multiplication, other things like that. The next thing actually to go over is going to be your RSI, or in our case, an ESI, which is our source index. The source index, or the ESI register, is typically used as source index for any string operations or just another general purpose register. An example of using ESI would be copying a string and then load the memory addresses of the source string into ESI. So I guess a good example of this is, say we wanted to move the offset of a source, or like a string named source, and then we wanted to say offset and then source. It would basically take that string and its offset and store it into ESI. This will load the memory addresses of the source string into ESI. That is going to be the same as your RSI. Now we have the, actually down here, stack pointer, base pointer. There was somewhere I wanted to go based on this. Give me 1 second. Should I do here? Nah. Look, because I had my notes somewhere for this. Right, so because this presentation was a little bit messed up on this side, I'm going to read from our base pointer and our stack pointer. Just go to RSP and RBP, or in our words, EBP and ESP, because of the type of assembly we're using, and go from there. So our EBP is the base pointer, is commonly used as a base pointer for accessing parameters and the local variables within the functions that were pushed onto the stack. Recall that we actually went into the stack frames and we pushed the function data on the stack within the stack frame. The RSP, or the ESP pointer, would be helped to push data onto that stack, or whoops, accessing a function parameters on a stack. So if we wanted to move the EBP or the base pointer or RBP to the current stack pointer, enabling the access to the functions, we would just tell it to basically move the value of ESP into EBP. So move EBP, ESP, and go from there, and that would be our base pointer. Our stack pointer, I kind of went out of order here. The RSP is the stack pointer, and in our case, it is ESP. But the ESP register will basically point to the top of the stack and would be used for managing the stack memory in assembly. Now, like I mentioned before, stack memory in a high-level form can't really be manipulated, but in the case of assembly, it's most likely going to be manipulated through stack pointers and even base pointers and working through different registers. So in this case, the stack pointer would just point to the stack to manage the stack of the memory. So an example of this would be pushing data onto the stack using something like push, which will push the contents of the specific instruction or the register we put onto the stack. So in this case, it would just be like push EAX, and we'd be pushing EAX onto the stack. The EIP was the next one I wanted to talk about. R8 and R15. Those are all just other general purpose registers that are going to be stored for or used to store information or data. The EIP is another one I actually missed in here, but that is the instruction pointer. The EIP register is the one register that contains the memory address of the next instruction to be executed. An example of kind of looking at it would be using it to be jumping to a different part of the code, like using a jump instruction to jump to, say we have a label like label, then we would jump to that label, and our EIP would basically be telling the code, hey, this is your next instruction to execute. And in that case, that's where EIP would be directly. I forgot to mention this, but the E at the beginning of every register stands for extended. This is because of transition from 32-bit assembly syntax to 64-bit assembly syntax, or in this case, x86 to 64, brought completely different changes in the register naming convention that they used before, and capabilities into the addition of the R prefix to register names, such as RAX, RBX, and RCX, and even RSI that we said. So this distinguishes the complete 64-bit version we had, which would be using the E, because the 64-bit version of the registers has their 32-bit counterparts. That was kind of something I wanted to clear up here. I didn't get a chance to fix that, but just for a little bit of clarification, the instructions still stayed the same, but they are just used, in this case, this would be the x86 64 version of assembly, or 64-bit assembly version of assembly, and then the other one would be the 32-bit assembly syntax. Since we're using like EIP and ESP, that would be the 32-bit assembly syntax. Talking on this syntax, something I also wanted to mention is that there's many different forms of syntax directly for assembly, but one of the two main common ones you will see are going to be your, what do you call it? Your AT&T syntax and your Intel syntax. Those are pretty popular here, and I actually want to pull up an image here to show you what AT&T syntax looks like versus the Intel syntax for people who aren't directly worth it. This is a good example here. Download it, default. So in here you can, wow, that actually came out worse than I actually thought it was going to be. Trying to find a better example. That's not so frustrating. Yeah, I guess that's kind of the way. It's kind of hard to see here, but you can see that this on the left is the AT&T syntax, because it uses the percent symbols, so percent RSP, percent NDI. So that actually looks like percent RSP, like that on a notepad. And then if you wanted to use like LEA, you would use like, in this case, in the image 1010, then parentheses and percent RSP and other things like that. The Intel syntax is much more cleaner when it comes out to that, because it has a whole different structure to it, and that's why Intel syntax is more preferred. So in a sense of what we would be seeing for our crack, that's what we will pretty much see, is that Intel syntax, because that would be the default dump of everything. Right, so now that we're done with our registers and we got that out of the way, we now have our operations. Like most programming languages, assembly has some form of operations that you can do mathematically. These are going to be known as your arithmetic and logical operators for x32 and 64-bit assembly, and you have the different things. I'm sure all of you guys could probably tell what some of these are. You have the addition, the subtraction, the multiplication, the integer multiplication, division, integer division, and so on from there. Data types are something I don't think I had the time exactly to go into today, but since we're going to finish assembly soon, I will kind of replug back into this and reroute on the second part of the presentation. But the pretty much base thing here, you have your addition, the subtraction, which will subtract the values, add the values, multiplication, your integer multiplication. And do note again that these are data type based, so your multiplication is going to be your unsigned, and then you have your signed integer multiplication respectively through that. You also have the same thing for division and integer division, signed and unsigned division, which is going to be your IDiv and div in this case. Then you have the logical instructions for bitwise operations. These confuse people a little bit. Even in normal programming language, they are quite confusing. So I kind of want to go over them a little bit, kind of brief over them. So the AND instruction will perform just a bitwise AND operation between the values of EAX and EBX and store the values and results in something like EAX, which in this demonstration I actually have pulled up. So let me work up and say EAX, so I can actually recreate that on this notepad. Yeah. So that would look like this, where you have that AND operation. Again, it will perform a bitwise AND operation between the values of EAX and EBX and store them in the result of our EAX. So this case here is adding to the EAX register. We're taking the values from the addition or the AND and then putting it into the EAX register. Again, going back to that left side kind of rule. The same thing falls for OR. We can do the same thing with OR. We just type OR, and this would perform a bitwise OR operation between the values of EAX and EBX and store the results in EAX in our case. So for people who don't know, the logical or bitwise OR operations are basically this logical disjunction that takes two binary inputs and produces a result that if any of the input bits are 1, the OR operation will produce a result of 1, and if both inputs are 0, the OR operation produces a result of 0. This operation is still a bit confusing, so I will probably write it down and kind of note it, and then paste what I have for notes for that to help people out with that. XOR is a similar way, but this is also known as exclusive OR. This is a bitwise operation that basically takes the values of EAX and stores the results, or sorry, EBX, the values of EAX and EBX, and stores them in the EAX register. This XOR will just pretty much add an X to this, so we have XOR EAX and EBX. For context, the XOR operation is a little bit different. It basically states that if two input bits are the same, if two input bits are different, one is 0 and the other is 1, the XOR operation produces a result of 1. And if the two input bits are the same, both 0 or both 1, the XOR operation produces a result of 0. So it is that exactly the exclusive OR. Since I didn't go over this, the AND is another bitwise operation. For that, the AND logic is, I guess you can say the AND logic behind AND would be to take two binary inputs and produce a result based on the logic that basically says if both inputs are 1, the operation produces a result of 1. Vice versa for 0. Goes that way. The next thing you have, these are logical and arithmetic shifts. This is more computer science, but these are just your shifting. So you have SHL, which is your shift left. So pretty much you would shift the bits in the EAX to the left by 1 position, filling the rightmost value with 0. So this would actually look like this. SHL, EAX 1. Whoops, I forgot the comma. That would pretty much be your shift left. And then you have your SHR. I'm going to actually go in vertical here. The SHR is a shift right. That would actually look like this. So you have your SHR EBX in this case. EBX. This is because your SHR register shifts the bits in the EBX to the right by 2 positions, filling the leftmost bits with 0. And then you have your SAR shifting the bits in ECX to the right by 3 positions, filling the leftmost bits with the sign bit. This is a little bit more to go into, but that instruction again looks like SAR, and then we would switch this to ECX and then 3. That is pretty much what that is. And then your SHR, or your shift on left, which would be B, finding my your SAL. So your SAL is I'm trying to think of a better way to explain this. It's your synonym shift left. It is just the left shift multiplies and goes on from there. It's a little bit harder for me to explain because this one is kind of hard to go into without technical terms. But that is a decent overview of your arithmetic and logical operators. As far as like normal programming languages, we have our conditional jumps and our controls. This is known as control flow in a programming language, and instead of just saying if else, else if, and then chaining a bunch of maps and stuff together, assembly has jump conditions. So your jump if equal JNE instructions, they should be pretty much easy to understand. But just to go over them, I guess a better way to start from the top. Jump if equal would be your standard if x is equal to so-and-so. So let's say we have x is equal to true, which is a Boolean value. If we wanted to say x, then that would be pretty much our equivalent of jump if equal. Our jump if not equal would be pretty much jump if x does not equal true. Jump if 0, this is a little bit of a different thing because this has to use with the pretty much CPU flags. And it depends on the way it's structured as well in the program. But jump if 0 is just another condition to jump if a value or the result of a flag is not 0 or is 0. J and Z is the same thing, but if not 0. Jump if above and jump if below, they are pretty much different flags as well. We find a good way. If you say jump if above or below a specific value, then you can basically create that block and execute that code. The jump if greater and jump if less than, those are also integer based. So if a value is greater than or less than or is greater, then you would say JG or JL. And then jump is just your standard jump instruction. You can think of these as literally just your jump instructions or standard conditional if-else statements or if statements. They act based on if a condition is true or if a condition is false or if a value is of a specific range, which in this case like JZ or JNZ would be 0. The call in your system calls are also something that you'll see a lot. So we can actually look this up a little bit more. Let me see. Pull up a better image of syscall. So your system call is going to call a system call, pretty much. Your syscalls, basically you have to set up functions for the system call before, for example, clearing a screen. That is a whole different system call that you have to set up. But your calls are actually the calls of functions. These are going to not call the direct function names, but rather call addresses in the memory space from there. These calls and syscalls are different. One's a system call, and one actually calls an address within the code. That is not a system setup call. Your ret, or your return address, is just going to be the return address from a function or returning from a function execution. That is pretty much all for your control flow. As far as like basics x32 64-bit assembly goes, but that is one way to put it up. So yeah, pretty much that's all we have to go over for assembly. As far as stack and base operations and memory access, you have your standard ones, pop and push. I think we got a pretty good firm of where we are popping data from the stack or we are pushing data into the stack. Those are going to be your stack-based operations there. And then you also have your mob instruction. The mob instruction I talked about a little bit more let me go back a little bit up to it. That instruction is just moving values into a specific register. So if you wanted to say, move the value of EAX into ECX, you can go back and you can say move ECX and then EAX, which will take the value of EAX and put it into ECX. It will just do that, pretty much move around memory. This operation is pretty important, and you see it a lot because there are such limited registers that sometimes you need specific calls and specific instructions to tell you where to move data so you can push data properly. Then you have your other function, which is LEA. LEA is another one that you'll see a lot. This basically stands for load effective address. It basically calculates the effective address of a memory location and stores it in a register. Um, an example of this would, I mean, this is going to be a little bit more weirder to see. But let's say we wanted to create some mathematical expression. So we say max plus RBX times 2. Oh, geez. Times 2. RBX. So basically, this will calculate the address of RAX plus RBX times 2 and then store it in our RDI address here. So this is pretty much just known for loading specific addresses in memory. That is one way to work around it. Um, so as far as actual assembly instructions go, that is pretty much it. Pretty much it for this part anyway, as what I have for this presentation and what actually goes on. Felt like I could have explained it a little bit better, but just to sum up what this part of the presentation was about getting you super beginner level into how assembly works and how programming languages work in applications.